In this video, we'll be looking at how to convert polar and rectangular equations instead of just looking at the ordered pairs. So there'll be equations that have x's and y's changed into equations that have r's and thetas and vice versa. Just so that you have an idea in mind of what a polar equation looks like, it's any equation that has r's and thetas in it. So this is one example of a fairly common polar equation. And rectangular equations are what we're usually working with. An example of this one would be something that has x's and y's only in it. So we're going to learn how to convert back and forth between the two different equation systems. So first, let's talk about going from the polar form into the rectangular form. There are two different strategies for doing this, and you should make yourself familiar with both of them. Sometimes either strategy can be used, but there are situations where only one strategy can be applied, so you need to know both of these. The first strategy is to do substitutions. We've talked about some formulas that say x is equal to r cosine of theta and that y is equal to r sine of theta. So you can perform a substitution, replacing anytime you see an r times cosine with x, or replacing r times sine of theta with y. That would get rid of your r's and thetas in your equation and change them into y's, for example. The second strategy, which is also often pretty easy to set up, sometimes you might just want to multiply both sides of the equation by r. If you have r to the first power on one side of the equation, then multiplying it by another r would turn it into an r squared. And then that way you can perform the other substitutions we have where r squared is equal to x squared plus y squared, for example. So sometimes multiplying everything in the equation by r and then setting up your substitutions will make an easier solution for you from there. Now, when you use this strategy, you usually do need to use completing the square because you're going to have something like x squared plus 4x. So I'm going to do a quick review for you on what completing the square looks like. So this is only for using that second strategy. You may end up in a situation where you have something like x squared minus 12x. Well, we want to get it into a factored binomial form. So what you do is you take half of the middle number, which is -6, and you square that. So in this case, that would be plus 36. And you actually need to add that number to both sides of the equation, but I don't have an equation here, so I'm just showing you the completing the square part. Once you do that step of taking half of the middle number and squaring it, you can write this in a different form by saying x, and it was whatever half of the middle number was. So in this case, -6 was the number that I was squaring. So you can rewrite x squared minus 12x plus 36 as the binomial x minus 6 raised to the second power. And you can check to see why that works. If you FOIL this out or expand it out, you should see that you get x squared minus 12x plus 36. Here's another quick example that I wanted to show just because I know it's a bit uglier when it's not a number you can easily divide by 2. So in this case, what's happening is we're getting the fraction -5/2 because I'm taking half of that middle number. Don't do it as a decimal. It's easier to keep it as a fraction. And then I said that you square the number. So we did half of this was -6, squared is 36. Well, now I'm squaring -5/2. So just think of it as -5/2 times -5/2. That means you end up adding 25/4. Because when you multiply a fraction by another fraction, you just go straight across. So -5 times -5 and 2 times 2. The factoring still comes down the same way I described earlier. It's just going to be half of the middle number, which we said was the -5/2. So the factoring for this expression here comes down to x minus 5/2 in parentheses squared. So that was just a quick review of completing the square, which is used for the second strategy I showed you on the last slide. So here's a quick example where we have been given a polar equation because it has r's and thetas in it, and they're asking us to change it into an equivalent equation, but they want it to only have x's and y's in it. So you'll notice that on one side of the equation, I have an r to the first power. This is where I was saying that it's useful sometimes to multiply everything by r. So r times r is r squared. And then if I multiply this expression by r, this is just one term, so I'm going to write it as 4 times r times cosine of theta. Now that we've multiplied both sides of the equation by r, I see that there are some substitutions I can perform. Because remember, an equation I gave you guys earlier was that r squared is equal to x squared plus y squared. So that's me doing a substitution for r squared. And whenever I do substitutions, I like to use parentheses. It doesn't really matter on the left side, but it could matter in other places. And then over here, I have 4 times r times cosine of theta. Well, r cosine of theta was something else I could tell you. I told you you could do a substitution for. R times cosine of theta is equal to x. So that way we've changed our equation into something that only has x's and y's in it. Now, usually we do want to manipulate these things around. We want to move everything to one side. So I'm going to rewrite this as x squared minus 4x. I'm doing opposite operations, so I'm subtracting 4x to the other side. And I'm going to leave a blank space and write plus y squared equals 0. So the reason I left a blank space here is because this is my setup where I want to perform completing the square. I don't have to do it for the y's because I do not have a y to the first power, so there's nothing to complete the square on. But for this piece, I have an x squared and an x to the first power. So I said that you take half of the middle number, which is -2, and you square it. So in this case, that's plus 4. But you can't just add 4 to the left side of the equation. That would mess up the balance of our equation. So I also have to add it to this side as well. The reason we do that is because it turns this trinomial into something easily factored. So it's going to be x and half the middle number. And then sometimes you'll have to do completing the square with the y's as well, but this one didn't have a y to the first power. So again, I'm just leaving it as the y squared part. So this equals 4. This will hopefully seem familiar to you guys. This is back in that circle form that we studied earlier in the year, where we have x minus a number squared, y plus or minus a number squared, and then this over here would be the radius squared. So we've written the rectangular equation form of a circle. Here's another example, but on this one, even though it looks very similar to the last, I'm actually not going to multiply both sides of the equation by r. When you see one of your reciprocal functions, so the secant, cosecant, or cotangent, what you actually might want to do is rewrite that using our other rules. Cosecant is the same as putting sign in the bottom of a fraction. So that's our reciprocal rule. Cosecant and sine are reciprocals, so I can instead write this as -2 divided by sine instead of multiplying by cosecant. Well, for my equation, remember opposite operations are to multiply by whatever you have in the bottom. So if I multiply both sides of the equation by sine here, then I end up with r sine of theta. So now I have r sine of theta is equal to -2. And this is one of those pieces I was saying you can form a substitution on. R times sine is equal to y. So we are done. This is a rectangular equation. It only has x's and y's in it. So we do not have to do anything else. That's why it was better to notice in this case the reciprocal function can be rewritten as dividing by sine, and that way we don't have to go through a lot of other steps to get our equation with only x's and y's in it. So your equation might not have an x and a y in it. It might only have one or the other. That can happen sometimes. And that means, if you remember from Algebra 1, that means that this is a straight line graph. So it's horizontal and it crosses through the point y at a height of y -2. So now we're going to look at converting equations the other way around. So now we're going to take equations that have x's and y's in them and change them to equations that only have r's and thetas. So the first thing you want to do is expand. If there's anything that you need to multiply out, like maybe there's some stuff inside of parentheses squared, go ahead and expand those things out. And then do your substitutions for x and y. And then your last step is just solving for r. So get r by itself on one side and move everything else to the opposite side. So here is our equation that only has x's and y's in it. I don't have anything to expand here because I don't have any binomials in parentheses being squared or raised to the third power or anything like that. So I'm going to go on to the next step where I perform substitutions. So now we're doing this backwards. It used to be whenever I had an r cosine of theta, I replaced it with x. But now I'm going to do it the other way around. I'm going to replace x with r cosine of theta. And then same thing for the y. I'm going to replace any y's I have with r sine of theta. So on the left-hand side of the equation, I have two terms now. I have 3r cosine of theta and 4r sine of theta. Since both of my terms on the left-hand side have an r in them, I'm doing the GCF factoring here. I'm taking that out. So if you take r out of this term, you're left with just 3 times cosine of theta. And if you take r out of this term, you're left with just 4 times sine of theta. And I haven't done anything to the other side of the equation. It's still just equal to 2. Now we're trying to solve for this r. We want it by itself. So the opposite of multiplying by a number is dividing by it. Yes, this is a big, long, ugly number, but the rule still applies the same way. So it's r times all of this stuff in parentheses. I'm going to divide that number to the other side. So 2 divided by 3 cosine of theta plus 4 sine of theta. That's my final answer. We now have an equation that doesn't have any x's or y's in it, and we have solved for r. So now this one does have some binomials being raised to the second power. So if you look back at the instructions I gave you, I said expand if needed. This is when it is needed. It is when you have some stuff inside parentheses being raised to a power. So we're going to FOIL that out. We're going to distribute it out. Then we'll do our substitutions and start solving for r. So on this first piece, we just need to expand x minus 3. You might want to write it out as x minus 3 times x minus 3. And do the same thing for y minus 2 times y minus 2. Or you can use the shortcut that when you have a binomial squared, it's the first number squared, 2 times the first times the second, and the second number squared. So here's what I got from expanding this out. I have a squared, 2ab, b squared, and then I did the same thing for the y's. A squared, 2ab, b squared. So our next step, I'm actually going to do a little bit of rearranging here because I have an x squared plus y squared. So if I group that stuff together, that's actually a substitution I can make. And then I'll also have some x's and y's that we'll plug numbers in for in a minute, but there are some other like terms and things I can do to clean this up first. So to describe my work here, I took the x squared and the y squared and I pulled them off to the side because I'm going to do a substitution for those in a second. I left negative 6x as is. I left negative 4y as is. But then here I did the combining of like terms. 9 plus 4 is 13. So I have 13 on the left-hand side, which I subtracted over to the other side and canceled the 13 I currently had over there. So basically the 13 on the left and the 13 on the right canceled out. So now I'm going to do my substitutions. Again, the x squared plus y squared piece here combined, that's actually just going to equal r squared. And then whenever you have an x, remember that you can replace that with r cosine of theta. And whenever you have a y, so I have negative 4 times y, so negative 4 times, y can be replaced with r sine of theta. So there are other ways to approach this problem, but I like kind of planning it out ahead of time and seeing that some of my pieces can be rearranged and canceled out to reduce how much work I had for the next step. Otherwise, if I just did the substitution right away, it would have added a lot more work and computation for me. So now we're going to get on to our factoring step. I have 3 different terms here separated by plus and minus signs, but all of the terms have an r in them, which means I can factor that r out. So if I take r out of the first piece, that leaves me with r to the first power. I'm taking r out of this, so that's negative 6 cosine of theta. And I'm taking r out of this, so that's negative 4 sine of theta. Then, remember that we have something called the zero product property. If you have 2 numbers, I have one number which is just r, and then the other number is all of this stuff inside of parentheses. Those 2 numbers are being multiplied together, set equal to 0, which means I can solve for the one on the left and the one on the right separately. So if I write r minus 6 cosine of theta minus 4 sine of theta and set it equal to 0. Remember, our goal here is that we're trying to solve for r. But now that I'm just working with this one piece of the equation, it's a lot easier to see that all I have to do is add the 6 cosine of theta to the other side, doing the opposite operation, and I'm adding the 4 sine of theta to the other side. That way I have my r by itself on one side of the equation. So it's a little bit tricky here is that I seem to have 2 different equations. Now one of the equations is just r equals 0. Well, that would be a dot, basically, just sitting at the origin. This other one is a slightly more complicated equation. This one seems to be setting up a polar equation that has a circle drawn. And remember, our rectangular form, this one was describing an equation of a circle with the center at 3, 2, and a radius of square root of 13. So if I'm considering these 2 equations that I have drawn right here, the one that seems to match my rectangular equation is actually just this one. So I'm going to ignore the r equals 0 one because that one doesn't really seem to match my rectangular equation. So that's it for the notes. Do keep in mind that you may have to pick which of the equations seems right. Basically, it's going to be the one that actually creates a polar equation. The other one's just a dot on the graph, so you can ignore that one. So that's it. Thank you guys for following along.